Welcome back, physics fans. Here we are on the third lesson of work, power, energy, and we're going to be talking about the conservation of energy. What? We're losing energy? I don't have the energy to continue. Well, let's just quickly go over what we learned so far in lessons 1 and 2. And work is force times distance, and that the force vector and the distance vector are to be in the same direction. And if not, then we have to use the cosine of the angle in there. And work is a scalar. An object lifted a height has energy called potential energy, gravitational potential energy, and that's calculated as mg and h is the one that's changing here. An object that is moving has energy stored as kinetic energy, 1/2 mv squared, 1/2 times the mass times the velocity squared. And our work energy theorem here right now is that when work is done, there's a change in energy. We've already been experiencing that and seeing that. And that an object that has energy has the ability to do work, that the change in energy can go back to work, right? So work is energy and energy is work. And they're both measured in joules. Okay, and what's important is the change of energy. If I ask you how much potential energy it has, you have to go with respect to what? Where it is, zero potential energy. Okay, conservation of energy. In any transfer or transformation of energy, the amount of energy is conserved, constant. We have many types of energies. We have kinetic, gravitational potential. There's already a spring potential there that we haven't talked about. And mechanical energy, and these are mechanical energies. The mechanical energy is the sum of the kinetic energy, potential energy, and spring energy that an object has, and it's used to do work. In other words, it is the energy the object has because of its position, its motion, or both. There's non-mechanical energies, and that's like heat, sound, chemical, light, electric, nuclear, magnetic. And just read through that. We're not going to be dealing with that much except maybe with friction. But the idea here is energy is always conserved. It might switch from one type to another type. And that's the switching is sometimes called transform or transformations. However, the total energy of a contained system will stay the same. It's conserved. And that's the big idea here. Some transformations are relatively easy to go back and forth, mechanical energies, and that's why we're easily dealing with that. And then some are not so easy, putting it to heat, and that's really hard to go back from heat to kinetic and stuff like that. And some of these other ones are harder. Oh, chemical, that's like a battery, chemical batteries. Okay, you can take the chemical out and get electric, and then the electric turns a fan, which is back to kinetic. So you can do it. The total energy at one point must equal the total energy at another point. Okay? And the total energy is just the sum of these kinetic energies. It could even be heat energy. So at one point, the potential plus the kinetic, maybe at the beginning, has to equal what the potential and kinetic are at the end. Another way of looking at that is that mgh, the potential plus 1/2 mv squared, the kinetic energy, is equal to a constant. Conservation of energy. Or at point A, you add up the potential and kinetic, and that has to equal the potential and kinetic at point B, and the potential and kinetic at point C, and the potential and kinetic at point D. It's conservation everywhere. Now, if there is energy loss, now it's not really energy loss transformed into the non-mechanical one, like friction to produce heat, then we have this one, that the potential and kinetic beforehand goes to the potential, kinetic, and heat afterwards. So it's just split up between these three different bins. Okay? And if it is not a conserved, meaning we don't have a little system that we're looking at, but we're adding energy to it. So if you're doing work to it by an external force of the system, then there is no conservation of energy. You're just adding more energy into it. You're pushing something along. If you're pushing something along, you're doing work. Then you have the initial potential, initial kinetic, and then that has to equal the final potential plus the final kinetic plus the heat energy that's produced. So what you started with is right here, what you added is there, and what you ended up with is here. Okay? Now, another way to look at it, and although this is probably the best equation, this one I've just kind of really jumbled up and messed up on. I like that one the best. If I put the initial over to this side, it becomes a negative. So if I take this kinetic and put it over there, and that'll be negative kinetic initial. So final minus initial, that'll be the change in kinetic energy. And if I take the potential over to here, initial, and put it over onto this side, and then I get potential final minus potential initial, but final minus initial is the change. So if I knew the changes, instead of all these 4 different things, but if I knew the changes, these 2 things, I could use this formula. And if it was conserved system that I was not doing any work, this would be 0 on this side. So 0 equals a change plus the change. And if there was no friction, if this was no friction, then 0 equals that plus that. That means the change in potential energy has to equal the negative the change in kinetic. If this goes up, this has to go down, because I add them together, the changes together, and it has to equal 0. I know I'm going very far and very fast, but maybe you're getting it. Okay? Now this is just the worksheet. We start working through it, and we're not allowed to do kinematics. We're starting so simple. We're not adding any friction in there, and kinematics is easy to do and can solve these. We're not going to try them. We're going to use our conservation of energy formulas, because as soon as we start adding friction, like here, you won't be able to use kinematics anymore. Okay? So, a heavy object, mass 2.5 kilograms, not that heavy, is dropped from a vertical height, dropped 8 meters. What is its speed when it hits the ground? Sounds like a good kinematics question. We're not doing it. We're going to do the energy. So the energy before equals the energy after. Okay? And the energy before is potential energy plus kinetic energy. And the energy afterwards is potential plus kinetic. Now I'm going to measure from the ground, and I don't have to tell you if I'm doing that, but I'm going to have to tell you if I'm not measuring the ground from the potential energy. So is dropped. So when it reaches the ground, that means the final over here afterwards, this is 0, because mgh is 0. When it reaches the ground, potential energy, final, has to equal 0, because this is 0. And what is the speed when it hits the ground? That's what we're trying to find out. KE is what we're trying to find out, KE final. So initial potential energy is mgh. So mgh, mass is 2.5, g is 9.8, and the height is 8. The kinetic energy, it's dropped, so the initial speed is 0. So the initial kinetic energy is also 0. So plus 0 equals 0 plus the kinetic energy final. So let's just figure out what this number is. 2.5 times 8, and that'll be 20 times 9.8, 196. Let's just do that. Hold on. 2.5 times 8 times 9.8. Yep. So 196 joules is the potential energy beforehand. And that has to equal the 1/2 mv squared in the final. And that's what we're trying to find out, is the final. So 196 is equal to 1/2 mass. So 1/2 times 2.5, and then Vf squared. So Vf squared is equal to 196 multiplied by 2, divided by 2.5, and that'll be VF squared. And now square root it. And that gives us the speed of impact. Yeah, we could have done it with kinematics, and it would have been faster, maybe. But we're trying to understand the power of this. Conservation of energy. Because as soon as we start losing energy to friction, we don't want to have to do kinematics, because that's really tough. Brutal. So 7-kilogram bowling ball dropped. So try that. And a physics student is dropped. I don't know why. Maybe you're next. If they reach the floor at a speed of 3.2 meters per second, what height did they fall from? And no kinematics. And then there's a question, do you need the mass? Let me just do this one a little bit. So potential energy initial plus the kinetic energy initial is equal to potential energy final plus kinetic energy final. So they're dropped. This is 0, and it lands at the ground. That is 0. So mgh is equal to 1/2 mv squared. Now, they're not equal. They're equal in that the initial potential energy is equal to the final kinetic energy. What the potential energy is when it begins is what the kinetic energy is when it ends. So, do you actually need the mass? No, actually, if you can take a look, mass is on both sides. We could cancel it out. If we do cancel it out, then the numbers we get here will never be in joules, because mgh is in joules. If we get rid of m, gh is not joules. So it's nice to actually have it. So if you are given the mass, then use the mass. But if you're not, like this one, then you'll cancel it out. Okay? So go ahead and try it. And try number 4 as well. I'm going to do number 5. Let me set this up. So here we are, question 5. A 15-kilogram child pushes himself at the top of a 3-meter high slide. His initial speed is 2.5 meters per second. His final speed at the bottom is 4 meters per second. What amount of energy is transferred to heat energy due to the work done by the force of friction? So we have this boy at the top of a tall 3-meter slide, and he's pushing himself off at 2.5 meters per second. So he's going down. We don't know the angle, the slope. We don't even know if it's considered the straight line. It's just wavy. And when he reaches the bottom, it's 4 meters per second. So how do we handle this? Well, we go back to this one, because this adds heat energy. So it's potential kinetic plus potential equals potential kinetic and heat. So the energy before equals the energy after. So potential energy initial plus kinetic energy initial has to equal potential energy final plus kinetic energy final plus heat. And that heat is what we're trying to find out. What is that energy stored up in heat? Now, this is a simplistic one. A heat, it could be sound too, because there's lots of sound produced as he was his bare skin was rubbing on the hot metal. That was not very slick, painful. Anyways, it could be lots of stuff. So mgh plus 1/2 mv squared is equal to mgh final plus 1/2 mv final squared plus the heat. Okay, so this is going to be 15 times 9.8 times 3 plus 1/2, 3, nope, 15, he's 15 kilograms, small little child. And V, he starts off at 2.5. And that equals M, which is 15 times 9.8 times the height of 0, right? We're setting the potential energy to be 0 at the bottom because we measured this from 0, from the ground. So he reaches the ground, 0. That's nice. That term disappears. 1/2. The mass is 15. And it's 4 squared plus heat. Now observe, you can't cancel out the masses here because there is mass involved in here, but we don't see the formula. Okay, so we can't cancel out the masses. So up comes Mr. Calculator, and it's good. We're going to turn on, and here we go. 15 times 9.8 times 3. We get 441 joules of potential energy plus 0.5 times 15 times 2.5 squared, and that's 46.875 joules of kinetic energy. This is 0, and this is 16 times 1/2 is 8. 8 times 15 is 120. Okay, so the total energy beforehand, I'm going to add those up. I'll go plus 441. So the total energy beforehand is 487.875. And that has to equal 120 plus heat. Now, if there was no friction, then his kinetic energy would have to be 487.875, which means his velocity would be a lot more than 4. But as slides go, there's a lot of friction on them. Unless you sit on a skateboard on a slide. Don't do that, it'll hurt. So I now have to subtract this 120. And I get that the heat energy is equal to 367.875 joules through conservation. And we couldn't use kinematics here. Great question. Great question. Great formula. Yes. So sweet. You'll use this a lot. And a lot of them, especially in Physics 11, this will be 0. They won't have friction in there. So pretty slick. Okay. Thank you for watching. Try out the rest of those questions. Enjoy the jingle.